In this session, I'm going to talk about the hierarchical linear models. So, obviously, the major objective of this session should be how they are better than the regular linear models that we have used to predict a quantitative variable. What are the kind of improvements that we are typically looking at when we are using a hierarchical linear model? So this is what we talk of. Why do we really need to get into hierarchical linear model? What are the limitations of the linear model for which I am looking at hierarchical linear modeling? Then basically we'll try to understand some of the concepts associated with hierarchical linear modeling, where we'll be using some words called fixed effects, random effects, the mixed effects, some such kind of words. So we have to understand what each one of them are. Then we'll take a data set, right? Based on that, we'll try to perform conjoint analysis, which is one of the major applications of the hierarchical linear modeling. So for this data, I can typically look at if I perform the linear model, how will my output come? Based on that, what is the kind of improvisation that's happening when I'm going with hierarchical linear modeling? Within that, I would try to look at what do I mean by simple hierarchical linear model versus a complete hierarchical linear model. So this is what is the context of this particular session. First thing, let's understand, when I create a linear model, I have taken a set of input variables. I have taken a set of outcomes, which is my dependent variable, and I have tried creating a model between this and this. The model will give me some coefficients. Those coefficients are exactly similar for all the input data, right? We'll use the same formula to predict for each one of them. So there is no randomness. So based on the sample of the respondents that we have got, we are creating some coefficients a plus b1 x1 plus b2 x2. Now b1, b2, a are constant for all the data. There is no randomness associated with a, b1, b2. Now that is what is the linear model all about, right? We have created a model based on a sample of respondents. Whatever the coefficient that came out as an outcome of the model, they are more and more the same for all the respondents. If I have to do the prediction for any of the respondents, we will simply take it as a plus b1 plus b2 kind of stuff. Whereas in a hierarchical linear modeling, what we say is there is some portion of the model which is having a population level effect, which means which will have the coefficients which are similar to every observation. But at the same time, we also have some portion of the model which will have an individual level effect. Means the coefficients differ. So when I am talking of effect, if everything is a population level effect, which means the coefficients are the same for all the observations in the data. Whereas when I am talking of the individual level effect, which means the coefficients, I have a flexibility wherein I can create the coefficients of the model separate for each individual. So this is where I am trying to understand an overall population level effect versus an individual level effect. Now that is where we are calling as the hierarchical linear modeling. So the coefficients are not uniform across. So whichever the coefficients I want them at a population level, they will be uniform for all the respondents. Whereas whichever the variables I am taking as individual level effect, the coefficients for them will be different for each individual. So the main assumption that goes into it is individual effects follow a distribution across the population. So the effect, so probably one specific person, two specific respondents, their effects also separately they follow a distribution across the population. So based on that, the coefficient for each of the individual for those particular variables will be changing. But at the same time, let me make it very clear that it is not a guess, right? Whatever the coefficient that it gives, it's not a fully random or it's not a full guess. Whatever the algorithm that is, it fits the overall model to all the data, and based on whatever it has fitted. So first the overall effect is being fitted, and based on that, after it has fitted the population level model, then there is a determination of the best fit for each individual within that overall. So there is first an overall fitment, and once the overall fitment is done, the individual level fitment is typically being done. So once the overall parameters are observed, then an individual level fitting is happening at each individual data level, and based on that the best fitting model is coming out. So which means it's not, the coefficient is not a guess, though I said it follows a distribution across the population. It's not a random guess that is taken as the coefficient, it's again a best fitted value itself. But let me tell you very clearly, this point is very important when we are using the hierarchical linear model. The data set for the HLM at an individual level needs multiple observations per individual, because based on that it will try to identify the random nature at each individual level, which means I need to have for one particular, if I want to do it at particular individual level, there should be multiple responses which this particular individual might have given. So there could be something to do with the ratings, rankings. So the responses could be across time. So today's response, tomorrow's response given by an individual for a particular aspect. So it should be the responses across time or multiple responses at one time. I give 10 different products. I want you to give a rating to each of the 10 products or 10 attributes. Generally, the most common example is I give a set of attributes to products, right? I give a set of attributes to the products, and based on these attributes, I want to rate or rank which one do you find the best, which one the next best. I want you to give some kind of ratings to the combination of the attributes. And based on that, I'll try to assess your individual level effect along with the entire population level effect. So when I'm trying to use the HLM, there are two things that are necessary. One, I need to look at the responses over time. Either that has to be the case, or I have to look at the multiple responses at one time. So there should be something that is repeating. So only then I can use the hierarchical linear modeling. So I am doing a survey with repeated measures, right? I want to find out what is your opinion for product 1, what is your opinion for product 2. Again, it's not a product. I am taking a composition of the features, right, which could be different products. So I am trying to find out the opinion on multiple items. So the best example for this is a conjoint analysis, which is widely used in marketing, but it can very well be used in the other areas as well. So multiple items, I am asking the respondent to rate at one time. So probably I'll say feature X, Y, Z, A. So there are 4 features I am talk of. Within each of the features, right, probably I'll talk about, let's say, the color of the car, the make of the engine size of the car, right, the length of the car. So probably a blue colored high powerful engine small car. So our red colored low powerful engine, low engine size, but again a small car. So there are some kind of attributes that I am giving, And based on that attributes, I am asking the persons to either rate it or rank it. And based on that, one, try to understand the overall population level effect as well as the individual level effect. For this purpose, we are using what is called as a conjoint analysis. But here, a lot of people will say, why can't I simply go ahead with a linear regression by treating each of these variables as grouping variables? So treat each of them as factors, and based on that, why not I build a linear model? Get the coefficient for each of the models. But that is not the case here. We are more trying to look at the integrated effect by the combination of each one of them. So I can very well get it into a much different aspect. I get into a geographic region, store wise, sales product wise, a lot of these kind of things. At any level of group level, I can very well work out that particular group level or individual kind of differentiation with respect to the overall hierarchy. So I can look at region wise if I want to build a model. So there is a generic plus something specific for a region. There is a generic something specific for my store. All I require is the store needs to have multiple transactions from a store I may have to capture. Similarly, salesperson, multiple transactions from the salesperson I have to capture. But again, I can do a overall model along with a salesperson specific kind of a model. So some variables can be taken as common across the entire model. Some of the variables can be allowed to change across the individual level attribute. So that is what goes as a part of hierarchical linear model. The reason why we are calling it as hierarchical is at one point there is an overall model, more and more relating the entire group, and on the other side we have an individual level model built after the overall population model is being built. So this is the reason, because there is a two-step, we are calling it as a part of the hierarchical linear modeling. And as the conceptual part of it, some of the some of the jargon that we really need to specialize here. One, when I say fixed effect, that is something, those coefficients, right, those variables whose coefficients are same for the entire population. So the effects that are same for every respondent, the coefficients will be the same for the whole data. So when I am talking of a general, the regular linear model, all the coefficients are constant for all the data, which means all the coefficients are fixed effects only. All the variables are fixed effects there. But when I say random effect, I have to make additional adjustments. So I am making adjustment for an individual level or a group level. So I can make it at a single respondent level, or I can do this work across a particular geography, which is a kind of a group. So I can use it at an individual or a group level. So there will be some kind of an effect. Apart from the overall fixed effect, some random effect exists. So for each, after the system has really estimated the overall population level model, it is improvising, or it is making an adjustment to the coefficients at the individual level. And the major assumption here is the random variables that follow a distribution around the fixed estimate. So whatever the randomization that we are getting, under the assumption that if this is my fixed estimate coefficient, my actual estimate could be anywhere between this and this, but at the same time it is not a random guess, it's a best fitting estimate according to the individual. As I have already said, initially the overall model will be fitted, and after that, by taking only the individual level observations, again a best fitting model with respect to the overall model will be considered. So random doesn't mean that some random coefficient will be given. It's only that it will change for each individual separately. And in some cases, we have something called multi-level models. So the only thing here is the individual as well as the full sample are at different levels. So first full sample work is being done, and out of that, whatever the full sample estimate comes out, on the top of it, the individual level estimate is being performed. So it's a subset of mixed effect model. So the total effect that we are talking of for each respondent is having two parts here. One, an overall fixed effect, which is primarily coming because of uniform coefficients across all the respondents, and along with that we have an individual level random effect also combined into it. And in some cases we can have nested models wherein the factor that we are typically looking at, it will occur only within subgroups of the total, within some subgroups of the total sample itself. So we don't find them across, right? Let's say we are talking of in a simple nested model, we are looking at the sales with respect to different promotions. So I have given different kinds of promotions. I am looking at the sales that are occurring at different stores. So here I am looking at sales purely because of promotions, whatever the different kinds of promotional offers that I have created at different stores. So we can very well look at what is the effect of the store. This store wise I'll call it as a random effect, right? Because for every store it has to be a separate variable. So I want to look at the store as a separate effect. That is why I'm calling it as a random effect, because there are different sales for different stores. And the promotion, I can take the effect of promotion within each of the stores separately. Now this is where I can bring in as a nested effect. So I want to take out the sales separately. Within the sales for each of the stores, I will look at the impact of promotion as a part of it. So which means they are not completely segregated kind. One is there inside the other. So that is what is typically another kind of model that I can build, which fall under the heading of the nested model. So all these things typically come out as the hierarchical linear models. So let's start exploring a data, take a data set, and based on that try building the model and trying to interpret the same. So we'll take one data, the ratings based data, right? So let me load my data set. So this is the data wherein I can look at the dim of this data. I called it as HLM. So 3200 records are there and 6 columns are there. So let me take the heading of this, the header of HLM, the first few records, just to understand what it is. So there is a respondent ID, right? So we are talking of a respondent. So there are so many occurrences for this respondent. So that's the group that we are talking of. If I want to take the tail of HLM also, just to see what it gives. So there is a respondent 200 here. So I think there are 200 respondents altogether in this data. 200 respondents, that is the data all about. So they are trying to give some kind of ratings on different attributes of a particular product, right? Different attributes of a particular product. I think this is about a roller coaster, different attributes of a roller coaster that needs to be brought in at a fun park. So there they are trying to consider the different attributes. So the speed of the coaster, should it be 40 miles per hour or 50 miles per hour, 60 miles per hour? So you can very well take the structure of HLM. You could really see that the respondent ID is an integer 1 to 200. They have given ratings on a 1 to 10 kind of a scale. The speed is also integer 40, 50, 60. Similarly, the height at which that coaster, roller coaster has to really go around, I think it's 200 feet, 300 feet, 400 feet, some kind of heights that are being talked of. Then we are talking of the construction type. Should it be steel or wood? It's a factor with two levels. And similarly, the theme of that coaster, should it be a dragon or a eagle kind of a scenario. So these are the things that they have captured. So on a combination of these four, speed, height, the construct and the theme, they have asked 200 respondents to typically provide their rating on a 1 to 10 scale. So here also the speed and the height, it would be better that if I take them as factors rather than as numbers, right? So probably I can take HLM dollar response ID. I'll take this response ID also as a factor, HLM dollar response ID. So I'm converting it into a factor. Similarly, I can do HLM dollar speed. Also, let me consider it as a factor of HLM dollar speed. Right? These are instead of numbers, it's better that they are factors for me. Similarly, I can take HLM dollar height also as a factor. I'll say as factor because there's no point in taking them as numbers, they are just choices. So it's better that they are factors. Now if I look at the structure of HLM, yes, it's coming much better now. Right, 200, 300, 400 are the factors with 3 levels. Speed is also a factor with 4 levels, I think 40, 50, 60, 70. So these are what are typically coming out for each one of them. Now, the respondent has to give, I think 200 respondents, so probably 16 combinations have been presented to each of the respondents. So that's where the size became 3200. Right, there are 16 combinations of speed, height, construct and theme have been presented to all the 200 respondents, and they were typically asked to provide their ratings on the same. So I can very well know which combinations of features out of these four, which combination, okay, what speed is being preferred by a lot of people, what is the height that is being preferred, what is the construct that is preferred, what is the theme that they are preferring. So I can very well understand which combination of the features is the most popular according to the preference of the customers. Now I have 200 customers overall in the data. So based on the kind of preference of the 200 customers, I would like to see which combinations of the features will be more and more popular. And I can very well go ahead with a linear model as well. So I can very well capture the rating for each feature. I have captured the ratings and I can build a linear model directly and I can implement it. I can very well say those four are a part of those four, speed, height, I can take them as predictor variables. The ratings that the customers have given, I can take them as the dependent variable, and I can very well build a linear model as well. Right, I can very well build a linear model as well, and based on that I can understand which feature is more and more preferable for each of the customers. I can simply go ahead that way. So if I really want to see what is the rating that people have given on each of these variables, I can use an aggregate function, right? Height wise, what is the average rating that the customers have given? Speed wise, what is the rating that the customers have given? I can very well do the average rating for each one of them. So let me use the aggregate function just to understand. Right, I can very well or the other way I can look at is I can do a summary of HLM directly. If I do a summary of HLM, okay, few things. The respondent IDs, each one is having 16. So which means 16 different combinations have been presented to each of the respondents for the rating purpose. The ratings, I have minimum value of 1 and a maximum value of 10. Those are the things that each one has typically presented. Speed wise, I could see 40 is the speed. So 40 speed, there are 800 times in the data. 50 speed, there are 1200 times. 60 speed, there are 800 observations, and 70 speed, there are 400 observations. Similarly, height wise 1400, 1200 and 600 per 200, 300 and 400 height. Make wise 1400 steel, 1800 wood, and theme wise dragon is 1600, eagle is also 1600. So this is what is the structure of the entire data, right? Is the values of the entire data. Now I can very well take the aggregate ratings. I can very well take the aggregate ratings. So I'll take aggregate of, I'll look at the rating HLM dollar rating, right? I'll take the aggregate average rating. So across the HLM dollar speed, for each of the speeds I want to look at what is the rating, and I want to take the mean rating. So it has to be a list. Okay, so I'll take list of HLM speed. So I could see here for 40 the average rating is 3.59. For 50 speed the average rating is 5.04. For 70 speed the average rating is 8.16. So I could clearly see that the average rating is much higher for a speed of 70 compared to speeds of 60 and 50. So there is a kind of an understanding that I can come to. Overall, there are a lot of people who are preferring having a speeds of 70 miles per hour. Now what about the height? How are people perceiving the height? Okay, the average rating is 3.6 for a height of 200, 7.25 for a height of 300 and 5.05 for a height of 400. So probably it looks like the most preferred height by the people is 300 feet. So 70 speed, 300 feet. Then what about the construct? Which one they are preferring more? When I look at the construct, it looks like they are not too much bothered about the construct. 5.21 for steel, 5.3 for wood, so more or less looking like similar. So they are not too much differentiated in terms of construct. Just at a quick outside view I am getting this feel. Then even when I am looking at the theme also the same thing. They are not too much worried. They are not too much having a different preference for dragon versus eagle. So this is what I could get at the first. So when I am looking at what kind of ratings they have given to each of the individual aspects, I could see that they are more particular about speed of 70 and going at a height of 300, but they don't have any specific preferences in general. This is not talking of individual. I'm talking of in general. They don't have specific preferences when it comes to the construct as well as the theme for it. But now I can integrate these four as a part of the linear model. Before I proceed towards a hierarchical linear model, let me take a simple linear model. So I'll call it as HLM underscore LM linear model. So I'll use the LM function where rating is my dependent variable. Now I can't use dot because I have to remove the respondent ID. So I'll simply say speed plus height plus construct plus theme. So this is what will be my independent variables, and the data I am taking as HLM. So this is where I am building my linear regression model wherein I can take my summary of HLM underscore LM. So here I could see that speed 50s, 60s, 70 are having a significant influence on the ratings. Similarly, height 300 and 400 are also having significant influence on the ratings. The theme eagle versus dragon is also having a significant influence on the rating. But the constant wood, the wood is typically not having any kind of significant influence on the rating. So I could clearly see that going with the coefficients, I could see that the most preferred one is speed of 70, then with a height of 300, right? Then because this is negative, they are preferring more and more of the steel, and even they are preferring the theme of dragon. So that's what is the typical construct that is going up. So I can very well take this information into consideration, and I can really go ahead in building my rating as well. Right? Probably I can take for someone who has mentioned 70 here, 300 here. So if I look at it, then whatever is his total rating, it is 3.07 plus. If he has given a speed of 70, then it is 4 point something. If he has given a speed of 300, then his rating is this much. And if he has given let's say steel and dragon, the other two will not be counted at all. So overall his rating is becoming 10.5, but our maximum is only 10. Now this is where I can't use a linear model, right? I get the contribution of each of the features to the overall model. I have got it very clearly that speed 70 is very important feature as a part of the overall model. So is the height 300. Now, when it comes to the wood, it looks like they are really indifferent between wood and the steel. So, which means either I can have any one of them. Probably I can now think of some other thing, not the customer preference here at all. Probably I can look at the cost perspective. Whichever comes more and more cheaper for me, I can very well go with it, because the customers are really indifferent in this case. Right? So when I look at a linear model up to this, so I could clearly see the preferences at the individual level. Here I could see that some of them are still preferring the 60 model. Some of them are preferring the 50 as a speed, right? But definitely all of them are preferring more than 40. The same logic here, compared to 200, there are a good number of people who are preferring 300, but some of them are preferring 400 as well. So there is some kind of a customization that I can go with. So that kind of thing doesn't come in the linear regression model at all. So different combinations are given to the respondents for different ratings. So I can give even the same combination to all of them, or I can give different sets of combinations to each one of them. But that is what will be the base for creating a hierarchical linear modeling problem. Now let's move towards okay, the linear model. I think I have already talked of, right? We have used the summary of the linear model. We have looked at how the features relate to the overall rating. That is what I have already executed. I got the average ratings for each attribute. That also we have evaluated, saying 400 is most preferred, 300 height is most preferred, 70 speed is most preferred. So we have got that linear model where we have taken all of them into consideration. So the coefficients indicate the association with the preference that we have already seen. Some of them have a very high weightage, some of them have very negligible kind of weightage. The height, the highest for each feature is chosen for the overall rating, and it can very well cross the extreme. It has got us 10.5 as the value, which cannot be possible at all. So simply interpreting the average result can very well be misleading. That is where the need for hierarchical linear modeling came into picture. The coefficients are estimated based on the design. So there is a desirable part, there is an undesirable. Some part of it the customer may not prefer at all, but still when we are using the formula for him, we take as if he has rated that. So it's not as reliable, especially when we are talking of extremes of preference. Different customers having a different set of preferences for each set of features. So sample level wise we are only talking about fixed effects being estimated, but in case of hierarchical models we can very well do an average preference wherein we'll take the overall fixed effect, but along with that we can also bring in the individual level customized effects for each individual or targeted towards a specific group. Now that is what we are trying to look at now, going with the hierarchical linear modeling. So within this I am going to talk initially about the simple linear model, simple hierarchical linear model, and after that we would also go with a very complex one, or otherwise we call as a complete hierarchical linear model. Where as far as the usage of it in R is concerned, it is the same thing, right? Whether it is simple or complete, we will be using this only. LME4 package is what we are going to use, and LMER function is what we are going to use for this. So let me install that package first. So I'll install the package LME4. Okay, so I'll load this package. LME4 is the name of my package. I'm loading it. Alright. Now, so here we have to see that we will get a hierarchical linear model. Now, what is this simple hierarchical linear model? Here it is like this. The overall population effect, the fixed effect is this much. The coefficients for fixed effect model are same for all the data. But along with that, only the intercept is random. Only the intercept part of it is random when I am talking of a simple hierarchical linear model, which means for each individual respondent, all the four coefficients will still remain the same, but the individual impact is reflected as a part of the intercept. So the intercept will be different for each and every individual. So because we have 200 respondents, we will have 200 different intercepts for each of the respondents, but the remaining coefficients for all the variables will remain the same. This kind of model is called as simple hierarchical linear model. So the individual randomness comes only in terms of the intercept, which is a constant. So we have fixed effects which are common for all the respondents, but per respondent will have a different intercept form. So that is what we are going to use now. We'll use the LMER function. Within that, I have to specify the terms, those particular variables for which I want the random effect. So in this case, I want the random effect only for the intercept. So that is where I'll set it as 1. That particular intercept, that particular variable for which I want the random effect for each individual, I will have to specify. I'll have to specify it this way. Along with my model, where I say the rating is dependent on the other four variables. Along with that, I also need to give what is my random effect. So predictors are the predictors which go as a part of the random effect I have to give. So intercept is the one I want to go as a part of the random effect, so I'll give it as 1. And then the separator, the group across what I want to give a separation. So here I'll take it as my respondent ID. Based on the respondent ID, so for each respondent, I want a separate individual intercept for each of the respondent. So based on the 16 observations that I have got for each of the respondent, I require a different intercept for each one of them. So this is what I have to specify into my model. So I have to give my grouping variable, which is what is the respondent ID, for which the random effect will be estimated. So the random effect, based on what I am giving as a grouping variable here, will be typically estimated for each unique group. So this is what, let's implement it first, right? I have already loaded this. So I'll call it as HLM underscore HLM. I'm simple HLM, SHLM. This is the variable I'm using. So I'll use a function called LMER, where my dependent variable is rating. The set of variables which are used for predicting, predictor variables, I am taking them as speed, height, I am taking the construct, and I am also taking the theme. So these are my variables. Along with that, I also need to give my random effects. So because it's an intercept which is going into the random effect, I'll simply give 1, then use my piping symbol, and I have to give on what basis, for what particular variable I really require the random effects. So based on the respondent ID, I say I want the random effects to come out. And the data in this whole case is HLM. I want to use this HLM data for this purpose. So there is a HLM model, simplified HLM model that is being created. If I want, I can look at the summary of this HLM model, HLM underscore SHLM. So if I look at the summary, okay, let's start right from the top. So linear model, linear mixed model fitment is being done. So this is the formula, we know this. Now you look at the scaled residuals, the minimum value is this much, the maximum value is this much, the residuals wise. The median value of the residuals is pretty much close to 0. Now you could see that the random effects, the respondent ID is an intercept. The respondent ID we are taking as an intercept. So this is what is the standard deviation that is present as a part of this respondent ID. So different observations having different kinds of standard deviation, different kinds of intercepts. So there is some level of standard deviation that is present in the intercept part. So group respondent ID, the groups that we are taking off is respondent ID, where there are 200 such kind of groups. Then looking at the fixed effects, these are the coefficients which we have seen more or less similar to what we have got even using the linear regression model as well. If you look at the linear regression, these are the similar coefficients that we have got there also. Right? Intercept, speed of this much, per speed 50, speed 70, we got it as 4.48. Height 300, we got 2.94. Wood is minus 0.11. Eagle is minus 0.74. Which is very clearly seeing that whatever the fixed effects that we have got here is exactly similar to what we have got in our linear regression model also. And if I am looking at the correlation between the fixed effects, this is what is the correlation that is typically coming out. So some of the output that comes out of this LMER kind of a model, these are the outputs. So the fixed effects, they are exactly identical to those that we have got using the simple linear regression model. But there is a unique intercept term which is an adjustment to this. This is again a fixed effect intercept. On the top of it, there is a unique intercept term which is made as an adjustment for each respondent. Now, if I really want to see what are my fixed effects, I use fixf. Fixf is fixed effects. I can use HLM underscore SHLM. So I'll get my fixed effects as this. These are the coefficient. For speed 50, this is the coefficient. Speed 60, this is the coefficient. So I can get the fixed effects for each of this. Similarly, if I want random effects, I'll use ranf. The same HLM underscore SHLM. Now this is where I'll get the random effects for each one. So you could see the intercept is different for all the 200 guys. For the first person, the intercept is coming out as minus 0.65. So overall is 3.07. And for the first person, it comes out as minus 0.65. Similarly, for the second person, it is minus 0.04. And for some people, it is plus. So these are the kind of adjustments that are typically being made at each individual level. So because 200 respondents are there, 200 different intercepts are typically computed. And now if I simply look at integrating these two and taking the coefficient, I can take the coefficient, right? I can look at the coefficient of HLM $SHLM. I look at the coefficient of HLM. So I need dollar respondent ID. I want okay. So coefficient of HLM $SHLM $resp.id. Right. Sorry. HLM underscore SHLM. I'm sorry. Coefficient of HLM underscore SHLM, if I'm looking at. So these are the coefficients that are coming out. Now let me see here. The intercept here is coming out as 2.42. Why is it? Why is it 2.42? Because overall intercept is 3.07 minus 0.65, making it 2.42. 3.07 minus 0.04. So it should be 3.03 or 3.02 for the second one. So the coefficient, the intercept is changing based on this. So the formula wise, you will have a different formula targeted towards each of the individual, which means these are all, this part from all these are fixed effects for each one of them. So the coefficients are same for everyone. But if I am looking at the intercept part is different for each of the individuals. So I can get the random effect where I get the per respondent random effect as a part of the intercept, and coefficient as a function. It combines both the fixed effect as well as the random effect and gives the overall integrated effect. So that's how we can really model the individual level preferences as well, depending on the kind of priority of a specific person, specific individual. We can have a completely different set of model in place. Now the same logic we can extend it, not just having the intercept as random. I can typically have almost every variable as a part of the random. So this is where we estimate the random effect parameter for every coefficient. Right? Instead of just taking the intercept alone, I can take almost every variable that I am using for building. I may want it for both, I may want to take the fixed effects of both as well as the random effects. Now this is where I can still use the LME4 package itself. The only difference being, when I did this part, here I have given the group, here I have given that variable which needs to be random. So what I can simply do earlier, instead of giving just one, I can add all the variables, all my predictors here. That's the only difference that I can simply perform. Now if you want, let me just redo this part. So I'll call it as HLM underscore HLM now, or CHLM, complete HLM. So all this I'll take the same rating versus speed, height, construct and theme. But instead of taking only the residual, only the intercept, I can still give all four of them. Speed, height, construct and even the theme. All four of them I can very well give as random effects with the respondent. So when I give this, it takes too much of a time for execution. So now I can very well give the same. Apart from that, everything else I keep the same. So this model becomes more and more complex compared to the simple hierarchical linear model. Now, few things we have to keep in mind when we are executing this. The estimation can be a very slow process because so many parameters need to be estimated. Too much of data is required. Even 3200 observations in this case might look like very small data. In some cases, it may not get converged at all. A stable model may not come out as a part of our output at all. Now this is where a few suggestions will be given, especially if I get some warnings. Let's see whether the model got executed or not yet. So there's a time that, okay, there are a few warnings that have come out. Right, in common arguments, max fun is less than 10 times length per square is not recommended. So the max fun is an argument. You increase it by a factor of at least 2, 5, 10. So probably you can put a control argument in the same where you can increase the max fun. So the max fun is looking like less than 10 times the length of par. So length of par squared. So it's better that I redo this model wherein I can set the max fun. Let me, but the default value is 10,000. But let me set it, right, the control value, let me set it as Elmer control. There is one variable that I am setting, wherein I can set the optional control level is equal to 10,000. So where I set the max fun as 1 lakh instead of 10,000. The default is 10,000. So let me set it equal to 1 lakh. So what typically happens is number of iterations to attempt convergence. Instead of typically going for attempting a convergence with 10,000 iterations, sometimes for this it may not be sufficient. So I would like to increase it by a factor of 10. So that is what I am saying here. Increase the control max fun argument by a factor of 2, 5, 10 and see if the convergence is coming. So let me try executing this. Right, or some other things you can look out for. Max grad is small, it should be much less than 0.001, or whatever the warnings you are getting, just Google them out as a part of the discussion forums and based on that just follow them. So there are different other optimization functions apart from your Elmer, so you have to really consider using the different optimization functions. And in some cases it's better that you collect more and more data. So what you are getting is, in case you are getting some kind of warnings, so these are the different things that you can very well think looking at. But because these are all the warnings, you can very well go ahead and look at the summary also, whatever you are getting with respect to the model. You can look at both the fixed effects, again the same, you can get your fixed effects, you can get your random effects for each of the observations, and you can also get the total coefficients as well. Let's see whether it executes now. But otherwise, once your model is created, you can get the fixed effects from the model by using the fixer. You can get the random effects. So you'll have a different parameter for each of the respondent here. And we'll also have the coefficient function which will pull out both of them, a combination of both the fixed effects as well as the random effects as well. So let it get executed. Based on however it gets executed, we can look at the output of the model. Let's see this time if the so whether the model is able to go further or not. But these are some of the things that we have to keep in mind when we are executing on multiple variables, making everything as a random effect. It becomes much more difficult as far as execution is concerned. We have to be slightly careful from that particular perspective. So now once the model is created, I can get the fixed effects of the model HLM underscore CHLM. I'll get the fixed effects of this model. I could see these fixed effects are still the same. Whatever we have got in linear regression, whatever we have got in simple hierarchical linear model, all these fixed effects are still the same. But if I want to get the random effect, now I could see that this random effects will differ per each individual. You see, for all the coefficients, they are different per each person. Right? If I look at here, there are some differences for each individual. The intercept is differing. The speed here is 0.82, whereas here it is minus 0.02. Right, the speed here, if I'm looking at the fixed effect versus the random effect, so the fixed effect is showing 0.82, whereas here it is becoming minus 0.2, which becomes 0.62. Same logic, 1.57 minus 0.12, it becomes 1.43. If you really want to look at, take the coefficients overall, HLM underscore CHLM. So this is what you could see here, 1.95, 0.61 is coming out for speed 50, because you could see overall is 0.82 minus 0.2, making it 0.61. So that's how the coefficients are changing for each of the individuals separately. So if I say their random effects need to be observed at each individual level, then we can very well segregate it based on the random effects as well. So that's how we use the complete hierarchical linear model to create one population level interactions. Along with that, I can very well go with individual level random effects as well. So these are the various things that we have considered as a part of this session. So we looked into the rating based conjoint analysis. We tried out the initial linear model. Then we have looked at both simple as well as complete hierarchical linear model. If you have any further queries regarding the same, you can very well get back to me by giving me a call on the number that I have provided below, or you can send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.